In this video, we're going to talk about differential equations that look like this or equivalently like this. So we're talking about a second order differential equation. You see the second derivative. It is linear though, so the second derivative is its own term, the first derivative is its own term, y itself is its own term. It's constant coefficient, so the constants in front of those three terms are just constants. Just numbers. They do not include the independent variable t. That's what makes it constant coefficient. And finally, it's homogeneous, meaning the final term, which we traditionally put on the other side of the equal sign, which doesn't involve y, is just 0. So not only does it not involve t, it's literally 0. That's what makes it homogeneous. Okay, so that's a really special, but again, very important differential equation that we really want to be able to analyze. Now, you can have a coefficient in front of the second derivative term or not. Of course, if you have it and you want to get rid of it, you can just divide through by a. That'll get rid of it here, turn it into a 1. The b will now be b over a, so that'll sort of be a new b. And then c over a, that'll be a new c. And of course, 0 will still be 0. So it's really easy to turn the first into the second if you choose. So I'll work with the slightly simpler second version where we assume we have a 1 in front of the second derivative. Now it turns out that the approach is you write down an algebra equation that comes from your differential equation. And the algebra equation goes like this. It goes lambda squared plus b lambda plus c equals 0. Lambda is the variable here. So we're replacing the second derivative with a lambda squared, first derivative with a lambda, and y itself with nothing, with 1. And we're keeping the coefficients the same. And this is just an algebra. This is just a quadratic algebra equation. It gets the official name of the characteristic equation of the differential equation. Okay, and you solve this. And it's a quadratic, so you can either factor or use the quadratic formula. And as we know, quadratics have there are 3 different ways that their solutions could come out. You can have 2 real solutions, you can have 1 real solution, or you can have 2 complex number solutions. And those complex number solutions are going to be conjugates. Let me just review those 3 possibilities real quick. If you solve using the quadratic formula, we would have negative b plus or minus the square root of b squared minus 4ac, but remember a is 1, so just 4c all over 2a, so over 2. And those are in principle 2 answers, 2 solutions, one with the plus and one with the minus. But of course a lot hinges on the b squared minus 4ac part that's under the square root. If the b squared minus 4ac part is positive, then you're taking the square root of a positive number and you'll get an answer, and then you can have plus that square root or minus that square root. So you get 2 real solutions. If b squared minus 4, I just wrote sorry, out of habit I wrote 4ac instead of 4c, which is what we're assuming. Okay. The second possibility is that b squared minus 4ac comes out to be exactly 0. So it's kind of very just exactly tuned. The b and the c are such that it comes out exactly to 0. Then you have the square root of 0, which is 0. So plus 0 minus 0, same thing. So you really only get one answer. In fact, you get negative b over 2 is what you get. And then finally, if b squared minus 4c is negative, then you're taking the square root of a negative number, which means I, right? You get an imaginary piece here. So you get negative b plus or minus an imaginary piece over 2. Now notice the plus and the minus apply only to the I part, to the imaginary part, and that's what we call complex conjugate. So you'll get one answer that, as with all complex numbers, it's a real part plus an imaginary part times I. But the other one will be the same 2 numbers, the real and the imaginary part, only the imaginary part will be negative. And that's what we mean when we say they're conjugate. That's in complex numbers, those are conjugates of each other. So we get two complex solutions like that. Okay, now what I haven't done is explained what these solutions have to do with the differential equation, but I'm going to go through each of these three possibilities now and explain how these solutions, whichever category they're in, will tell you the solutions to the differential equation that you're working on. So, two real solutions. Let's say that characteristic equation, when you solve it, you get two real solutions, and let's call them lambda 1 and lambda 2. So those are actual concrete numbers. So it turns out that in this case, the solution to the differential equation is a linear combination of two exponential functions, e to the lambda 1t and e to the lambda 2t. So arbitrary constant times the first plus arbitrary constant times the second. And the two solutions go in the exponentials as coefficients of the t's. Okay. Now, any initial conditions that you have can be used to then figure out what the a and the b are. But that's the solution to this homogeneous differential equation. So it's that simple. You solve that quadratic, you get these two answers, and you just fit it into this, and that is the solution. Now, let me take just a moment to explain why that works. Now, of course, we could just simply check it, but I'll kind of explain it in a slightly different way that kind of shows how we came up with this, because this so far is very arbitrary. If you go back to your second order differential equation, right? Now, the idea was, if you go to a first order, we learned from our experience of a first order differential equation. First order, linear, homogeneous, constant coefficient was dy dt plus cy equals 0. Or, of course, we could bring the cy over. That would be fine. But the point is, we know that the solution here is e to the negative ct. It was an exponential times an arbitrary constant. Since I'm using c here, I won't call this big C here like I usually do. I'll call it a. But again, the point is, it was an exponential function that worked in a first order linear constant coefficient homogeneous equation. So, when people first encountered this, the idea was, well, maybe exponentials work here also. So for the second order, we guess that the answer is an exponential with some number in front of the t. Let's call that number lambda. Okay, so sort of like with the method of undetermined coefficients, you make a guess and then you just plug it in and see if it can work, and if it looks like it can work, what that undetermined number has to be to make it work. So if that's our guess, then our first derivative would be lambda e to the lambda t, and our second derivative would be lambda squared e to the lambda t. And when you plug it in, then you get lambda squared e to the lambda t plus b lambda e to the lambda t plus c e to the lambda t equals 0. And all three of these terms have that e to the lambda t, so we can just cancel that, and 0 on the other side, so we can do it. So lambda squared plus b lambda plus c equals 0. So we find that, yes, this guess can work as long as the number we put right in here is a solution to this equation. The lambda has to satisfy this equation. And that's our characteristic equation. So that's why it really is sort of it boils down to, solving this differential equation boils down to solving this algebraic equation. So, and as we said, if there are two real solutions, so there's two different lambdas that work here. So on one hand, we would have e to the lambda 1t. On the other hand, we would have e to the lambda 2t. Those each would be solutions. And then it turns out that you can multiply either of them by any constant you like and it would still work. Right, that's true for the first order as well. And then, and this is new for second order, but it turns out if you add them together, you also still get a solution. So that was the motivation, and that's the idea behind this technique, and it's the reason why we look at this algebra equation for all the information we need. Okay, let's do a quick example. Here's our differential equation. It is one of the ones we've been talking about, second order, linear, constant coefficient, homogeneous. So we immediately switch to the corresponding algebra equation and we try to solve it. And you can use the quadratic formula, but of course if it can factor, that's a little bit easier. And this one can, right? Lambda minus 2, lambda plus 1, giving us two answers, -1 and 2. So these are the lambdas that will work, and remember the whole point is that means those are the exponentials that will work. So our answer, our general solution, would be a e to the minus t plus b e to the 2t. Given initial conditions, we could then solve for a and b, but I won't do that right now. Okay. So let's move on to the next case, one real solution. Here's our differential equation, and let's suppose that after switching to the algebra equation, we solve that and we only get one solution, presumably because, well, probably it's likely that you could have factored it to get this, but via the quadratic formula anyway, the part under the square root ends up being 0. So let's say we just get the one solution, let's just call it lambda 1. Well, for exactly the same reasons, we can say that e to the lambda 1 t is a solution, and any multiple of it is a solution. So we have that. But we can't be done yet, because this is a second order differential equation, which means it would come with two initial conditions. And in order to match both initial conditions, we need more than one arbitrary number. One arbitrary number we don't have enough freedom there to match any pair of initial conditions that can come our way. So there has to be another one. We need that second one with its own arbitrary constant, so that we have two of them, which we can then solve with two initial conditions. So there has to be this other one. Now, this one I will not explain as much, other than to say that, of course, if you plug it in, it will work. But it turns out that t times that same exponential will work. This does not work in the two real solutions case. You can't just multiply by t and say that that's a solution. It wouldn't be here. But it turns out in the case of one real solution, when you only have the one exponential, it's sort of a perfect case. You can multiply by t, and that is also a solution, it turns out. And like I said, all you have to do is plug it in to either this general one or like any specific one, and you'll see that it will work. So that's what we do. We again get sort of two independent solutions, and we put an a and a b in front of each, and we add them together, and that gives us our overall general solution. Okay, here's an example. Here's our differential equation. We switch to the algebra equation, and we try to solve it. This does factor. In fact, this ends up being lambda minus 4 equals 0. In other words, lambda minus 4 squared equals 0. We are only getting one answer. Lambda equals 4. All right, so we know what to do now. We say our overall general solution is a e to the 4t plus b t e to the 4t. And that's it, and that will work. Pretty easy. Okay. On to the final case. Suppose our second order differential equation, after we switch to the algebra equation, we solve it, and most likely it would not factor, at least not with nice clean whole real numbers. So we go to the quadratic formula, and the thing under the square root is negative. And so we get two complex answers, alpha plus beta I and alpha minus beta I. All right. Well, here's what the solution ends up being in this case. The real part kind of acts just like when we had two real solutions. So we have an e to the alpha t that's just based on the real part, not including the imaginary part. Now, how does the imaginary part work in? Well, it turns out that you get cosine of beta t multiplied onto your exponential. And now that's going to be one solution. We put an arbitrary constant in front of it. Your other solution will be the same, e to the alpha t, and then times a sine of beta t. So the real part of your solution goes into an exponential. The imaginary part goes into a cosine and a sine, respectively. Just a little bit of motivation for where the cosine and the sine are coming from. We could actually say that the answer was, like, we could treat this the same as the two real solutions and say, well, it's just going to be an exponential, but just with a complex number up there. So we could just treat this like case one and say, hey, it's an exponential. So that one and then that one. Okay, but then if we break this down a little bit, because we don't want to have a complex function. Let's assume that this differential equation came from some real-world scenario. All the quantities involved, the quantities that we're measuring, the quantity that y actually stands for, is a real number in the real world. So we don't want to have a function that has I in it. We would like to just have a real valued function. So although this may be mathematically correct, and it is, these two guys, we don't want to leave it like that. So after a little bit of manipulation, we can do this. We can write it as e to the alpha t times e to the beta I t. Okay. And then, so there's your e to the alpha t part, right, that we are writing down. Then we get to pull out something that we've learned in previous course, which is the exponential form of complex numbers, e to a number times I, which is what we have here. We can use Euler's formula, which says that e to a number times I is cosine and sine in that way. So cosine of beta t plus I sine of beta t. That is Euler's formula. I know there are a lot of Euler formulas and Euler methods and things named after Euler, but this is a biggie. This is one of the big things that he discovered. And hopefully you at least remember learning it at some point, whether it was recent or not. You can turn an exponential with an I in there into, kind of break it down into rectangular, a real part and an imaginary part. Okay, so now I won't keep working this out, but this just shows you where a cosine and a sine would come from. Now we still have an I here, I know, but then at the same time this guy will also do the same thing, but with negatives coming in. And when you include the arbitrary constants, you can make it be such that the I kind of goes away. I won't show you that right now, but it's hopefully now at least it's believable that this would be the form of a solution. And this solution, you see, doesn't have I in it anymore. Okay, so I'm sweeping a little bit of the details under the rug, but I just wanted to point out Euler's formula is where the cosine and the sine are coming from. Okay. And I'll do one example of this kind of differential equation. All right, so here we go. We do lambda squared plus 3 lambda plus 10 equals 0. Now, I don't see a way to factor that. Doesn't mean it can't be factored, but I think this one can't be. We go into the quadratic formula. Right, so we do negative 3 plus or minus the square root of 9 minus, and then we get 40. And then all divided by 2. And, oh, I didn't even intend for this to happen. This square root is going to come out nice. It is negative, right? Negative 36. but the 36 happens to be a perfect square. That was just lucky. So we get 6i, right? The square root of negative 36 is 6i all over 2. I'll just write that as negative 3 halves plus or minus 3i. Right, so our two lambdas, our two solutions are negative 3 halves plus 3i and negative 3 halves minus 3i. Okay, but the way that that morphs into a solution for our differential equation is we'll have a e to the minus 3 halves t, so an exponential coming from the real part, which is the same for both of them. And then we do a cosine of 3t, and then we just repeat it, but with a sine of 3t. And that 3 is coming from the imaginary part, plus 3 or minus 3. It doesn't matter which one. I mean, we always pick the positive one. You could pick the negative 3 as the one you plug in, but cosine of negative 3t is the same as cosine of 3t, because cosine is an even function. And sine of negative 3t is the negative of sine of 3t. So there'd be a negative out here, but you have an arbitrary constant here anyway, so that could be positive or negative anyway, so it really doesn't matter. So it doesn't matter whether you use the 3 or the minus 3, so just use the positive one every time, and it'll just look nicer. Okay. So we have more to talk about. I want to, in future either videos or written documents, I will do an example or two where we also impose initial conditions and see how to get the a and the b. I also want to talk about what these functions are actually doing, what their behavior is. So we'll look at the graphs of these functions. But this video was just the basics of getting that general solution down in the 3 different cases.